The question that I have is, could you define the compressibility parameters of soil? If you recall, we already defined what are called the compression index and swelling index, right? We noted that when E versus sigma V prime for a soil is plotted in a semi-log space like this one right here, you are likely to end up having a relationship that looks like this. Basically, we have a mathematical shape that consists of two straight lines. The first part is called the swelling line and the second part is called the virgin compression line. The slope of the swelling line, the parameter that appears in this equation right here, is called the swelling index, and the slope of the second line here, the virgin compression line, or the parameter that appears in this equation, is called the compression index. We also noted that the recompression curve is usually a little different from the swelling line, but for practical analysis they could be assumed to be the same. And therefore the same swelling index C sub S represents not only the swelling line but also the recompression line. And for that reason is also sometimes called the recompression index. So these two are compressibility parameters of soil that we already talked about. In this video, we will define two more. First, let's define what is called the coefficient of compressibility. Coefficient of compressibility is basically the absolute value of the slope of the E versus sigma V prime relation at a given point. Obviously, slope varies from point to point, and therefore coefficient of compressibility varies from point to point. Say we have a normally consolidated clay. Then we know there's a relationship between weight ratio and the effective vertical stress given by this equation right here, right? And therefore, we should be able to relate the coefficient of compressibility to the compression index C sub C. You won't be able to take a derivative of this directly. You have to express this in natural log. So I have a little side note here that tells you how you could do that. So the derivative of E with respect to sigma V prime works out to be this, and therefore the coefficient of compressibility A sub V is given by this equation right here. So you can see A sub B is a function of sigma V prime. The second quantity that I would like to define here is what is called the coefficient of volume change. This is basically A sub B but normalized with respect to 1 plus E naught. So in terms of C sub C is given by this equation right here. If we want to find these quantities on the swelling curve, all we have to do is to use C sub S, the swelling index, in place of C sub C. When we change the vertical effective stress, the weight ratio changes, right? So how does the change in weight ratio for a normally consolidated clay compares with that of a over-consolidated clay? Let's consider the following. Let's say we loaded a soil sample from point A to point B along the virgin compression curve by increasing the pressure by delta sigma prime. And during this part, the weight ratio is going to decrease by, let's just say, delta E. At point B, I unload it to point C. So it's going to follow the swelling curve, right? So portion of this change in weight ratio is recovered, that is this part right here, which I call delta E superscript E, is recovered. On the other hand, the remaining part, which is from A to C, is permanent. I'm denoting that part by delta E superscript P, P for plastic. So this is the elastic part, this is the plastic part. Now compare this with something that we are all very familiar with, uniaxial stress-strain relationship for a material, right? So here is the loading curve, here's the unloading curve. So when you unload it, for most material, this part is a straight line, right? So when I go from point A to point B, the stress is increased by delta sigma. There is a change in strain of delta epsilon. So that's the total change in strain. And then when we unload it, part of that is recovered, which we call delta epsilon E, E for elastic, and the remaining part, which I call delta epsilon P, is permanent. It's permanently lost. Now if we were to reload it from C to B along this curve, the change in void ratio is simply going to be delta E superscript E. So that is much smaller than the change in void ratio during loading from A to B. Another way of saying that is that if the soil had been normally consolidated, the change in void ratio as we increase the stress from this point to this point by this much, the change in void ratio is delta E. On the other hand, if the soil had been over-consolidated, for the same change in the vertical stress, the change in the void ratio is going to be much smaller. We'll see in a little bit that this change in void ratio is the one that translates into vertical settlement. So the vertical settlement associated with the normally consolidated clay is much bigger than the vertical settlement associated with an over-consolidated clay.